Hey friends, I'm going to take a couple of seconds and try and connect a couple pieces that Mr. Mark didn't quite hit on, and try and clear up some things, because we're getting into the middle of, are we talking about particles? Are we talking about moles? Are we talking about molecules? Are we talking about a mass? Are we talking about a molar mass? Just some terms and some ideas that we need to keep separate. So that was too many. The first one would be, how do I determine, sorry, let me get this out of the way. How do I determine the mass of one atom or one particle? A lot of times in physics we kind of make atom, particle, molecule, compound, those all tend to be a little bit interchangeable. We're asking for the mass of one really, really small thing. And so what we can do is we can find that number on the bottom of the periodic table. Often it will be given to you in a problem, but for carbon it's 12. And we have this unit that we call an atomic mass unit, or just U. So one carbon 12 atom has a mass of exactly 12 U. But that's not useful to us. We need it in kilograms. And so 1 U is the equivalent of 1.6605 times 10 to the negative 27th kilograms. This is on your equation sheet, so you don't have to remember this number, but we do have to know how do we convert back and forth. And so we just set up our fraction. We're going to end up multiplying by that conversion factor to get 1.99 times 10 to the negative 26 kilograms. That's a really, really, really small mass, but we're talking about a really, really, really small thing. What if we're talking about a molecule, a compound, something with more than one atom together, like water, H2O, or carbon dioxide, CO2? Well, if it goes, we just take all of the atomic mass units that we find from the periodic table for those compounds. So this would be carbon dioxide, CO2. Notice the little subscript tells us how many we have of each atom, and so we have 2 oxygens here. So we're just going to add those up to get 44 U, or 44 mass units for a molecule of CO2. Again, look at that factor. We're going to convert, and by multiplying by 1.66 times 10 to the negative 27th kilograms, and we end up with 7.3 times 10 to the negative 26th kilograms. Still very small, even though it's, 4 times bigger than a single carbon. Okay. Next, brief review into chemistry. If you're in chemistry right now, this should feel familiar. We got to talk about the mole. You would have done it in the spring of your chemistry year. We abbreviate mole by kicking out the E. It's just MOL, which I think is pretty funny. Do not abbreviate molecule because you will by nature then write mole, and then that will be super confusing. The symbol is a lowercase n, and the mole is equal to 3 things. It's equal to 6.02 times 10 to the 23rd particles. That's Avogadro's number. It's also equal to the molecular mass of each atom or each individual compound. And it's equal to 22.4 liters of an ideal gas. And this might come handy later, but that's a pretty easy conversion, the 22.4 piece. Okay, so how do we get to particles? Well, it's 1 mole is 6.02 times 10 to the 23rd particles. So if I'm given a number of moles, say 12 moles of nitrogen, notice that nitrogen is a diatomic element. Di means 2. So there are 2 nitrogens together there. Not that it changes anything here, but if we were looking for atomic mass units, we would have to look at double the amount of 1 nitrogen. Anyway, we have 12 moles, so to get it to cancel, we're just going to multiply by Avogadro's number to figure out the number of particles. And this is going to be a whole bunch of particles because there are 6.02 times 10 to the 23rd particles in 1 mole, and now we have 12 of them. Okay, we could also go backwards. If you are given a number of particles and you need to find moles, well, then you're just going to divide by 6.02 times 10 to the 23rd. Okay, what if I have the molecular mass? Well, to find the molecular mass, you're just going to use that number that's at the bottom of the table because the mass of 1 mole of carbon is 12 grams per mole. I'm going to come back, but you're probably saying at this time, wait a minute, I'm looking at 2 of these things. You just told me that was 12 U, 12 atomic mass units, and now you're telling me it's 12 grams per mole. And it's very true. 1 the first one, when we're talking about atomic mass units, we're talking about the mass of one particle in kilograms once we convert it. And so that's where 12 helps us. For the molecular mass, 12 is in terms of grams per mole. So 12 grams of carbon will be 1 mole of carbon. Okay, a little confusing, but you're going to use the same number. All right, so how do we determine that? Well, we're going to find the molecular mass. You do the same as you did with atomic mass units. If it's a compound, you have to add up all of the molecular masses of each individual atom. And then you end up taking the number of moles and multiplying, or taking your grams of sample and dividing. Kind of depends on what you have here. So this is really useful when you're in the lab, because I need to go measure out a sample of carbon. Well, I'm going to measure it in terms of grams. So if I had, I don't know, 24 grams of carbon, how many moles is that? Well, I would take my grams, 24, divided by the molecular mass, 12, and get 2 moles of carbon. Okay, so a couple other things. You might see the term standard temperature and pressure. That is just, we've talked about a little bit, but maybe I'm going to harp on it again. 0 degrees Celsius, which is 273 degrees Kelvin. That's standard temperature. And standard pressure is, for us, we just use 1 times 10 to the 5th pascals, but it's also 1 atmosphere. And so you can use any of those to convert back and forth if you want to. All right, so what about kinetic energy? Right? Mr. Mark spent a lot of time talking about kinetic energy, and he came up with 3 equations. One is a reminder from last year when we were talking about any object that's moving. It's got a kinetic energy. It's 1/2 mv squared. This could be for a big object like a car or a small object like an atom. And then he gave us the next equation, which is 3/2 times Boltzmann's constant times the temperature. So our kinetic energy is proportional to the temperature. And that would give us the kinetic energy of a molecule or a particle, something really, really small. But sometimes we might have it in terms of moles. Remember that Boltzmann's constant times Avogadro's number gives us this R, this ideal gas law constant. And so we have it in terms of kinetic energy of a mole, of moles of sample, which is 3/2 RT. I usually use the Boltzmann's constant. I find we tend to talk in physics more about particles than about moles, but it is useful to know both. So how do I relate velocity to temperature? Because we saw in the PhET relationship that if I increase the temperature, my particles were all going to move faster. And so is there some relationship between these? And yes, there is. Often we call this the root mean squared velocity because it's going to give us an average velocity of a particle. So we know that kinetic energy is equal to 1/2 mv squared. We also know that it's equal to 3/2 times Boltzmann's constant times the temperature, and so we can set those equal to each other. That mass term is the mass of a particle in kilograms, so you would use atomic mass units, or U, to convert if you didn't have the kilogram sample. And kilogram is kind of a big unit to use when we're talking about atoms, so you should always have really, really small numbers for your masses. If we do a little bit of rearranging, take the square root, we end up with an equation for the average velocity, which is the square root of 3 times Boltzmann's constant times temperature all over the mass. So if I were to ask what happens if I double the temperature, well, my velocity is going to increase by the square root of 2. What happens if I, increase my temperature by 16? Well, my velocity is going to increase by 4. And so we can kind of use this equation. It's not listed, I do not believe, in your equation sheet, but the other 2 are. And so if we can get back and forth between these 2, we know exactly how velocity and temperature are related. Okay, good luck.